Once again, welcome to A-Level Physics, Cambridge A-Level. Topic is deformation of solid. What have we covered? Right? This set, when we think of deformation in this topic, we are looking at change in length, either a decrease in length or increase in length. Right? 6.1 is stress and strain, and 6.2 is elastic and plastic behavior. Okay, we have covered stress and strain. We look at force on metal causing deformation. Right? We look at spring and spring constant. There's a formula for calculating your spring constant or apply to spring. And there's a formula to calculate energy stored in the spring. X is the extension, F is the force applied, W is the work done or energy stored. And we look at spring in series and spring in parallel. After that, for a spring, we use a spring constant, but then we come to metal, like wire, we find that spring constant is not a good constant because it depends on length of the spring and area of the spring. So we find our Newton definition of stress, strain, and Young's modulus. That's the definition for stress. It's the tensile force. That's the cross-sectional area. And that's the strain, extension of the original length. And that's the Young's modulus, stress over strain. And we look at the graph of force against extension and stress over strain. So now we are looking at, for this lecture, we will be looking at 6.2, plastic and elastic behavior, force on different material. Brittle, ductile, and polymer or polymeric material. Okay, so 6.2, elastic and plastic behavior. For the syllabus requirement, understand and use the terms elastic deformation, plastic deformation, and elastic limit. So these are the three terms that you need to remember if you are required to use. Understand that the area under the force extension graph represents the work done. Determine the elastic potential energy of material deformed from its limit of proportionality for the area under the force extension graph. Recall and use the potential energy formula half Fx half Kx squared of material deformed within its elastic limit of proportionality. Okay, in fact, we have covered most of that. Actually, we will review that. There's a force, there's extension, the elastic limit. Hooke's law states that extension of the spring is directly proportional to the applied force, provided the elastic limit is not exceeded. After the elastic limit is exceeded, the spring does not return to its original length, permanently deformed. Okay, so the elastic limit is slightly above that. Mathematically, force extension F equals to Kx. Right? And we can say K can be found from gradient of the graph. Basically, ratio. Right? K is called the spring constant or elastic constant, and it's called force per unit extension. Defined as force per unit extension. As the unit, Newton per meter, kilogram, as minus 2. Okay, and energy stored, energy stored in the spring. Work done is stretching the spring. That's a shaded area. That's a shaded area. Area of triangle, half fx. And if we replace the f, kx, we got half kx squared. Okay, let's go to ductile material. Force on different material, ductile material. A ductile substance lengthens considerably and undergo plastic deformation until they break. Such material can be stretched into a wire. In ductile material, initially the extension is proportional to the force applied, then a large extension for a small change in force. When the force is removed, the wire does not return to its original length. Example of ductile material would be lead, copper, wrought iron, steel. Right? That's a typical shape. Example, copper. Right? Manchester in that's the origin. That's the extension. That's the force. OP. OP is a straight line. In this region, Hooke's law is obeyed. P is the limit of proportionality. Right? It's from origin to P is a straight line. Hooke's law is obeyed. And we're going to say another point. E is called the elastic limit. It's just a point after the proportional limit. If the load is removed and the material up, right? So that means from P, from origin to E, where we add the load to add the force. Force is the load, right? Force is the load, or load is the force. We add the load up to E. We remove the load. It will return to the original length. That's how we know it is within. It's still within the elastic limit. Right? Of course, in this region, the force is not proportional to the extension anymore. Only OP. So elastic limit is the point beyond which the spring does not return to its original length when the load is removed. Right? So when we add the load, we call that loading. So loading means adding load, adding weight. Unloading means we remove the load. So if we add the load, the force of the load until X, Then unloading it, it will still follow the same line. It will still return to the origin. So if we keep on loading, adding load, B is called the fracture point or breaking stress. If that is stress, then this is breaking stress. Right? A fracture point is where the material breaks. Right? So from origin to this point where we reach the elastic limit, that's called elastic deformation. Means in this region, the material will return to its original length and when the force applied is removed. Right? In elastic deformation, when the force on the material is removed, the material returns to its original length. So after the elastic limit, it's called plastic deformation. Here it breaks. What's the difference? When the force is removed, the material does not return to its original length. Right? Example, you can take an example of the point there. Right? Just after the elastic limit, where we remove the load, it will not return to origin anymore. It will follow that line there. The arrow shows that we are unloading it. Right? This is where we are loading it. So the two are almost parallel. Brittle material, example, ceramic. Right? Brittle material breaks after the elastic limit is exceeded. There's no other portion anymore. There's the elastic limit. Right? Proportional to elastic limit. Extension is proportional to the force until it breaks. The material returns to its original length when the force applied is removed. Right? So, example of brittle material is ceramic and chalk. Materials such as glass that can be extended but do not show plastic deformation and will easily fracture are known as brittle material. So glass, chalk, ceramic are brittle material. They just break when the elastic limit is exceeded. Right? We don't have this broken line section. Polymeric material, example rubber. There are bonds between the chain, long molecules, and form the chains, which are broken when the material is loaded. These require work to be done, so that more energy has to be put in than got out. This leads to energy loss due to hysteresis, where we see the loading and unloading curve. We call this hysteresis. Right? Loading and unloading curve doesn't coincide. When the load is removed, the rubber does not return to its original length, as the changes are now straightened. Right? You don't need to know too detailed, just need to know that rubber extended, then it doesn't return to its original length. Right? So we can summarize the three: brittle, plastic or rubber, polymeric material, stretch easily, a little bit of force, extension a lot. Whereas ductile material, there's a there's a there's a there's an elastic limit, then there's a plastic. After the elastic limit, the whole region until it breaks is called the plastic deformation. Okay, interpreting graph for loading and unloading a wire. Right? We look at ductile material, force, extension. This is loading. The arrow shows we are adding load, we are adding weights. So what is X? Right? E is the elastic limit. Area X work done in elastic deformation. X, Y, Z. Right? Y is this area. Z is this area. So X area, Y area, Z is work done in loading. Let's say we load until S. Then we add the load until S, or we apply the force until S. Then we remove the load. Right? Remember, when they exceed, when the force exceeded the elastic limit, it will not return to the origin anymore. It will follow this line is roughly parallel to that line. Z, energy that is recovered in unloading. That's the energy that we receive back. XY is energy that is lost, energy that is converted to heat due to unloading, or we call it network done. Right? When you touch rubber, you find it warm. Or you touch a piece of wire where it exceeded the elastic limit, you'll find it warm. That is what we call network done. Network done is converted into heat. Material feels warm. Arrangement of molecules in the material is changed. Right? We don't need to know too much detail. So let's summarize. Deformation, force of metal causing deformation. Spring, there's a formula we need to remember. Right? Force proportional to extension. Energy, potential energy or energy stored in the wire. Spring in series. Remember, spring in series. Tension is the same for each of the spring as the load. Parallel, load is shared equally among the spring. Stress, strain, Young's modulus. Right? These are all the formulas we have learned. Right? You might want to draw your own summary so that you know what is covered. Right? Stress, strain graph. Area equals the energy per unit volume. Gradient is Young's modulus. Force on different material. Pressure force on different material. There's brittle, there's ductile, there's polymeric. Okay, let's try some question. This from past year paper 204 June. The diagram shows sign of weight. There's a sign. Weight is 20 newtons suspended from a pole. That's the pole. Attached to the wall. That's the wall. The pole is kept in equilibrium by a wire attached to X. That's a wire attached to X, attached to the wall, attached at point X of the pole. The force exerted by the pole at X is F. Right? The force exerted by the pole at point X is F. And the tension in the wire is 40 Newton. Right? So that is the weight of the sign, 20 Newton. Okay. Sign of weight, 20 Newton. So it's pulling down vertically downwards there. That's the weight of the sign. That's the tension. Right? The wire is pulling on the point X. 40 Newton. Right? So both of these are pushing inwards on the wire. Sorry, on the pole. So the wall is pushing on the pole. Right? That's the reaction F. Right? So we can draw on the diagram. Right? F is our weight. Sorry, our weight, we can draw it here. Then we have the three forces. There's the force from the wall. There's the tension. There's the weight. Right? Weight act vertical downwards. Tension direction of the string, pulling the pole upwards and inwards. The tension pushes the pole inwards against the wall. So tension is pulling it there. So it's pulling the pole inwards. The normal reaction, sorry, F is a normal reaction, so it should be stay strongly. That's the normal reaction F. That's the way. Rather than draw separately, we can draw on the diagram itself. Tension is already there. The normal reaction is there. So that must represent the weight. Then we choose which is the right answer. That's the right answer. That's the weight, 20 Newton. Okay, which of the structure, pole and wire, is under compression or tension? Right? Which is compressed, which is stretched. Right? We look at the diagram again. Consider the forces acting on the wire and the pole. Which of them is under tension and which of them under compression? Right? The wire, okay, remember the wire pulls the pole in upwards, actually pulling at an angle. So it's actually pulling upwards and pulling towards inwards there on the pole. The pole and the weight tries to pull the wire downwards. The sign there, trying to pull it down. The pole is not trying to pull it down. At the wall, the wire pulls on the wall. Wire is now, these are all pulling down. So the wire is pulling on the wall. The wall pulls upwards on the wire. The wire is under tension. Yeah, remember we are looking at the force acting on the wire, not looking at on the force acting at X now. We're looking at the force acting on the wire. So the force acting on the wire, okay, this one is pulling down. This holds the pole, the weight is pulling down. So it's under this way, pulling it down. And the wall is pulling it up. Right? So the wire is under tension. How about the pole? The tension in the wire pulls inwards. Tension in the wire is pulling that way there. So we can resolve it as one going, pulling it up, one pulling it towards the wall. The pole is pushing on the wall. The pole, that whole pole at this end there is pushing on the wall. So the wall is pushing on the pole there. So what are the forces acting on the pole? This force there, that one there, due to the tension. And we call the wall normal reaction on the wall, pushing it there. So the pole is under compression. Okay, what is the spring constant? and energy stored when the spring is stretched to 0.4 meter. Right? Spring constant, that's your F, that's your X. Right? Just take a point. K is just F over X. F is 20. Right? Any point? Right? Best is to take it as large as possible so the error due to your reading will be minimized. So it's 20 divided by 0.4. Use your calculator, is 50 Newton per meter. Right? I can use a ratio, still the same thing. Instead of using gradient, you can use ratio. Right? You can use 25 here, 25 and 0.5. We still get the same answer. Energy stored up to 0.4 meter, right? Remember, the area is this area, not this area. Right? But it's the same. In this case, it's the same. Energy stored is area of the triangle. That area. So it's half. That one is 20. F. That one is 20. That one is 0.4. So it's 4.0 joule. But you can use gradient. You can compare. Right? So in this case, it's more complicated if you use gradient. Unless it's practical, not necessary to use gradient. Okay? You can use gradient to solve it, but more work as well. Still get the same answer. Right? For experiment only. Okay, let's try a structure question. Take Hooke's law. Extension is proportional to force or load provided elastic limit is not exceeded. A spring attached to support, that's a support, and hangs vertically as shown in figure 6.1, that's a figure 6.1. An object M of mass 0.41 kilogram is attached to the lower end of the spring. The spring extends until M is at rest at R. Right? So it's not moving, it becomes at rest. So are the forces acting? The force of the spring, F, right? Pull it down, so the spring is pulling it up, and then the weight of the object M, that's the object. The spring constant of the spring is 25 Newton per meter. Show that the extension of the spring is 0.6 meter. So just use the formula. Right? For equilibrium, the force by the spring equals to the weight. The weight is mg. So m is 0.41 times 9.81. Get 4.02 Newton. And use the Hooke's law formula. Okay, put in your value. F is 4.02. Spring constant is 25. X, then from there you can calculate your X. The object M in figure 6.1 is pulled down a further 0.060 meter to S and is then released. For M, as it is just released, state the forces acting on M. What are the forces acting on M? Weight of the object pulling down, reaction force on the spring, or elastic force on the spring, which is equal to tension in the spring, pulling outwards there, two forces. Calculate the acceleration. Right? So we got the weight pulling it down, got the elastic force of the spring. The resultant force, Newton's second law, F equals to ma. So in this case, our F is greater than the weight. So now we are equal to previously. Okay, we pull it down to 0.06 meter. That's where we get it from. So that provides the resultant force. That's your K, this is your K, this is your X extension, and this is your mass times acceleration. Calculate your A. Describe and explain the energy changes from the time the object M in figure 6.1 is released to the time it first returned to R. Right? While the energy changes, elastic potential energy or strain energy, so as it's moving, right? Initially it has elastic potential energy. As it's moving, kinetic energy, and as it rises up, gravitational potential energy. As the extension is reduces, and the velocity increases, and height increases. Okay, that's the energy transformation that's required. Okay, that is 2003 June 22. The paper. A beam, the weight of which may be neglected. That's the beam. Don't worry about the weight of the beam. Visible. Is supported by three springs. There's your three spring. When the weight is hung on the middle of the beam, the weight W. The extension of each spring is X. The middle spring is, and the weight is removed. This one is removed. This one is removed. What is the extension when the weight of 2W hangs from the middle of the beam? Okay. Look at the forces acting on the beam. Right. All of them are the same. So it's F plus F plus F equals to W. Three springs share the load due equally to the force F on the spring, right? Or the tension in the spring is just W divided by 3. And that is equal to Kx, right? For each of the spring. For two spring, the force on each spring is right? Remember, we remove this one. So now we got two spring. And this is now 2W. So the force on each spring is 2W. Two spring is divided by 2. So it's W. Since the force is proportional to extension, that's your Hooke's law. When the force is triple, there is W. The extension is triple, so 3x. Okay. The answer is D. Okay. Okay, we are given some data. It's an experiment. The load F is used to stretch a steel wire of length L. Calculate the extension and its uncertainty. Okay, so we go to the formula. Here's the extension. FL over AE. Put in our F is 20, L 1.5, pi R squared, right? The diameter divided by 2, change it to meter by R squared. Young's modulus, that's Young's modulus. Convert it to SI unit. Calculate and give your answer. If there's no specific requirement, you can give whatever unit you want. Right? When you calculate that, it will be meter. You can change to millimeter. Okay. This probably this extension is very small. Very small to measure. Okay, go back to the formula again. Since you want to find uncertainty in the extension, and then replace our area with pi d square, right? With pi r square e. The percentage uncertainty in x, because percentage uncertainty in f, 4 doesn't is a constant, pi is a constant, so it doesn't have uncertainty. Plus percentage uncertainty in L, because the square, it can be R, it can be T, it's the same, it doesn't affect, right? In calculating percentage uncertainty, 2 because of the square there, and percentage uncertainty in D. Okay, we can just refer back to the data there. It's all given there. Okay. So some of you using calculator may have got 0.73, even use 0.73, doesn't matter. Or 0.72, we've got 0.72. So you got your delta x is 0.54. Remember, uncertainty is one significant figure only. Right? So you have to round it off to 0.05. So 0.73 plus 0.5. This is a stress strain graph. The shaded area is a straight line. The shaded area, what does it represent? Energy stored per unit volume. What does the gradient represent? Young's modulus. Copper wire of length 2.5 meter. That's the original length. And cross-sectional area given is fixed at one end. A load of 96 Newton is attached to the free end so that the wire hangs vertically. The Young's modulus of copper is 1.1 as 10 to the power 11 Pascal. Calculate for the loaded wire, the stress applied, the strain, and the extension. Right? E is given. Stress, go to the definition, force divided by cross-sectional area. Right? That's the force, the load. 96. Cross-sectional area is given. Use your calculator. 6.4 10 to the power 7 Pascal. Strain doesn't give you the extension, so you have to use the formula definition for Young's modulus. Because Young's modulus is given. Stress is there. Stress, there's Young's modulus. Then cross multiply. Take this one down, so across there. Then use calculator. It doesn't have a unit. It's just a ratio. 5/8 to 10 to the power minus 4. Then calculate the extension. That's what we have calculated. So our definition for extension or strain is extension of our original length. That is what we have calculated. Then the strain x is the extension. Original length is 2.5 meter. Cross multiply. Calculate out 1.5 millimeter. Okay. Do one more question. It's also a partial question. 2014 November. April 11. A rubber band is stretched by hanging weights on it on the force extension graph plotted from the result. What is the best estimate of the strain energy stored in the rubber band when it is extended to 30 cm? Right? Remember? The strain energy is the area under the graph. So we can just draw a triangle here, a rectangle here, a rectangle up to here, and there's another triangle here. There's a rectangle there. Strain energy area under the graph, half half 6 is here, 7 is there. Sorry, that's hidden. Maybe I can make this one smaller. Okay. Okay, there's a triangle here. Half, there's about 7 there, and then this is about 6 there. Roughly estimate because there's only one answer, they're quite far apart. And then there's another one here. This is 6. So this is a triangle here. There's your 15, 17 there. 17 minus 6 is 11. And then this is about 8. About 8 there. 30 minus about 22 there. Roughly this triangle. And then remember this one has to change to meter. That's why we have that. 10 to the power minus 2. So area of the rectangle is there as your 6 there. 6. Right. Remember this overestimate. Doesn't matter. We remove this some part here. 6 times 23. That one is 20. That's 3 there. answer is A. It's an overestimate. So the nearest one is 1.8. A. Okay, I think that's the end of the lecture. Yep, that's the end of the lecture. Thank you.